So this is going on page 116 when we're done. Okay, so this first part's just a quick little review of vectors. Vectors are not new to you. They are first introduced to you in geometry. And then for those of you that are in physics, you should have seen them in physics as well. So a vector is called a quantity. So a vector is a quantity that has both magnitude which could be size or length or direction. Size or length or distance is the other word I was thinking of. So a quantity that has both magnitude and direction. So a lot of times in physics, you're looking at it as distance and direction because it has something to do with your velocity and acceleration, all that kind of stuff. All right, so your geometrical representation, like what does it look like? It looks like a ray, looks like an arrow, right? But it is considered like a directed line segment. So this point P right here, that is the initial point, so that's where we start. So it can be called the initial point, or it can be called the tail. And then Q is where we end, but it actually ends in an arrow, and then the arrow just is kind of pointing to the point. Q is the terminal point. Or the tip. So if you've ever heard the phrase from tip to tail, it's a vector reference. All right, so then when we name them very much like we name rays. So vectors are denoted using the arrow symbol, and it always points to the right. It doesn't matter which direction the vector is going in or what's happening with the vector. The symbol doesn't tell you anything about the vector except that it is a vector. So this vector PQ can be named as PQ. I don't know why that's a blank space. I guess it disappeared. With the arrow on top, or the lowercase p, and there's an arrow there, but I don't know, it didn't really show up on mine. Or just a bold-faced lowercase letter without an arrow. Obviously, when you're writing it, that's not something that would make a whole lot of sense, but you can see it printed that way a lot. Okay. Then we have what's called a zero vector, and a zero vector is a vector with magnitude 0. So vectors give you distance and direction. They do not give you location. Ordered pairs give you a location, or a point gives you a location, but a vector is just distance and direction, and it could literally be anywhere. All right, so there's three types of vectors. Well, there's three types of vector pairs. Not really three types of vectors, but three types of vector pairs. And so this first one, we could have parallel vectors. They look a lot like parallel lines. They could have the same or opposite direction, but not necessarily the same magnitude. Okay, so they could have the same magnitude, but not necessarily. So if I have this could be vector A, this could be vector B. Right, so vector A and vector B, this kind of looks like one big blob of stuff, so there are my actual vectors. So vector A and vector B, and this here would mean that vector A is parallel to vector B. They go in opposite directions, they're not the same size, that's fine, but they're parallel like you would think about being parallel. Okay. Then we have equivalent vectors. They have to have the same magnitude and the same direction. So it would look like this. We could call these vector M and vector N. Again, it just looks like a big blob of stuff, so bless you. Bless you. There are my vectors. And so here we could say vector M is equivalent to vector N. Equivalent is just a fancy word for equals. And then opposite vectors have to have the same magnitude, but opposite directions. And the opposite of vector A is written as negative A. That's how you show opposite there. So we can do these two. We can call it vector U and vector V. And so here, vector U is equal to negative vector V, or the opposite of V. Notice all three sets are actually parallel, but the best category for equivalent and opposite are equivalent and opposite. So if they don't have the same magnitude, but they're going in same or opposite directions, it's parallel. If they have the same magnitude, then it's either going to be equivalent or opposite, basically. Okay, we good on that? Easy enough? All right, so let's use this graph below and classify each pair of vectors. So let's find vector A and vector E. So here's vector A, and here's vector E. Okay, well, clearly they're not going in the same direction, right? But they have the same magnitude, and you can count magnitude like slope. I go up one and over. Okay, so this kind of looks like E also, but it's actually C. It's where so make sure you pick the right one. It's confusing. I know they both kind of look like E because of where the line goes through. But so you can count, you can look at magnitude kind of like slope. I go up 1 and over 2, down 1 and over 2. So they have the same magnitude, but then they're going in opposite directions, which makes these opposite vectors. Then I and F, here's I, here's F. Okay, so they do look parallel. They're at least parallel. But then if I count, I'm going to go up 6 and over 2, up 6 and over 2. So it means they have the same distance and direction, which makes them what? Equivalent. Then D and E. Here's D, and here's E. I would say for sure they're not equivalent, right? They don't have the same distance, but are they going in the same direction? Yes, and you can tell that by slope also, because I can go down 1 and over 2, down 1 and over 2, and then down 1 and over 2 again. So that makes these what? Parallel. All right, so then B and G, here's B, here is G. Well, in order for them to fall under any one of those categories, they have to at least be parallel. Are those parallel? No, so it's not going to be any of that, so this is just none. And then C and H, this is C, this is H. So what do you think about those? Opposite, very good. All right, any questions on that? All right, good deal. Then grab your other piece of paper. And this is going on page 117. Okay. Now, vectors can be anywhere in the coordinate plane, okay? But we also do talk about them being in standard position. And then we'll look at them in any position. But in order for it to be standard position, that is when the initial point, what's another word for the initial point? The tail, good. The initial point, what is this? Initial point, or the tail, is at the origin. So it looks much like a radius did for our circles, whether they were unit circles or any other circles. If it's in standard position, it's a radius. And all of this stuff is going to relate all back together. So this does say if vector v is in standard position, which that one is, and we have a terminal point AB, then the component form, okay, so the component form is how you actually write a vector. It's in its little pointy bracket form, and it would look like this, A comma B. If you have parentheses, that denotes that it is an ordered pair that you plot. The pointy brackets means that it's a vector. You can start anywhere, but then you count and then you end wherever you're supposed to end. In this case, we are in standard position, so we're starting here at the origin. That's why it's just AB. But if that's the case, then here's something I know. I know that this length has to be A, and this length has to be B. And once again, we have a little right triangle in the coordinate plane. So it says the magnitude and direction angle of a vector given in component form can be found using the following. So magnitude, it looks like a double absolute value. That means the magnitude of vector v. The magnitude is the length. So if I want the magnitude of vector v, how can I use A and B to find the length of v? Exactly. A squared plus B squared would equal the magnitude squared, right? So if I want the magnitude, then I just take the square root of A squared plus B squared. And then I want theta. How can I find theta? Tangent inverse, exactly. So theta is equal to the tangent inverse of B over A. And isn't this literally what we just did with polar? And isn't this literally what we did before that? We were looking at any angle in the coordinate plane. It's the same stuff over and over again, and it's all related to each other. Okay? We good? All right. So let's look at number 1 here. I want to find the magnitude and direction angle for each vector. Oh, dang it. And I forgot to tell you when you came in to get your calculator. So send one person from your table to go get your calculators. Give them the numbers. Okay, now that we have that. So I want the magnitude. So the magnitude of vector r, like I still have to write stuff even though I get to use the calculator, equals the square root of 7 squared plus 24 squared. And then you can put that in the calculator just like that. And what do we get? 25. Okay, now we're going to find the angle. So the other thing is, for the angle, we are, with vectors, you're normally working in degrees. So we want our calculator in degree form. So you're going to push shift mode. And then I think it's 3 for degrees. Make sure you're in degrees. Okay, so then we want to find theta. Theta is equal to the tangent inverse of 24 over 7. Now remember that when you do this in the calculator, it's actually going to give you alpha. And then you have to figure out what to do with alpha. And you have to know what quadrant you're in. What quadrant would 724 be in, or pointing towards? The first. So then what you get is the actual answer anyway, right? So when you take the tangent inverse, what do we get? Good. 73.740 degrees. Okay, we all good with that? All right. So then on number 2, I want the magnitude of vector n. That's equal to the square root of -3 squared plus -1 squared. Now, that's what we write down because that's what we're doing. But when we square them, do the negatives actually matter? No. So in your calculator, you don't have to type in -3 and -1. Okay, you have to write down correctly what you're doing, but then you let the calculator do it. You get the magnitude of n is equal to what? Square root of 10. We good with that? All right, so then theta is equal to the tangent inverse of -1 over -3. Now those negatives cancel out, but even if they didn't, when we are doing the inverses on the calculator, what do we always type in? The positive numbers. We write down whatever it is, and it may end up being negative when we write it down, but you always type in the positive so it can give you alpha. So go ahead and take the tangent inverse. That's going to give you alpha, which is 18 something, right? But then what quadrant is our angle going to be in? Third. This is in the third quadrant, right? Negative, negative. So remember that we have to think about, all right, this is alpha. What do I do with alpha to get my third quadrant angle? This is pi, we would have subtracted alpha, and this is adding alpha, right? But we're in degrees, so we don't use pi, we use what? 180. So this would be 180 plus alpha. This would be 180 minus alpha. And this would be 360 minus alpha. So it's the same thing we did before. We just have to use pi and 2 pi instead. I'm sorry, instead of pi and 2 pi, we use 180 and 360. So for theta then, we should get 198.435 degrees. What questions do you have? All righty. Then you do number 3 on your own. And outside of class, if you're using a calculator that does not simplify square roots for you, then you have to know how to simplify the square roots. Decimals are not going to be okay. What questions do you have? Mm-hmm. What about it? Well, you go to the right and then down, so you're in the fourth quadrant. So I got to do 360 minus alpha. What else? Anything else? Okay, so we're not going to do all of number 4. Just tell me, what quadrant would this angle be in? Second. Okay, so once we get alpha, what would we do with alpha in the second quadrant? Good. 180 minus alpha is what we do there. Okay, make sense? Good? What questions you got? All right. Okay, so we were just looking at the vectors in standard position, which is like right here, but they're not always in standard position, because remember, the vector itself does not give you, in component form, does not give you location. It gives you distance and direction. If you were given ordered pairs to know where to start and stop, then you end up with location, distance, and direction. But if all you have is the pointy bracket component form, that doesn't tell you anything. But if you have the 2 ordered pairs, you can write it in component form. So this would be vector B here, be equal to And then you just do x2 minus x1, comma, y2 minus y1, and that gives you your component form. Okay, don't ever mix your x's and y's. So the component form for vector CD then would be 6 minus 3, comma, 3 minus 5. So vector CD is going to be 3, negative 2. That's your component form that would get you your magnitude and direction angle. We good with that? All right, then y'all do number 6. Find RS. Okay, -7, -9. Okay, so when we're talking about direction angle and I ask you which quadrant is it in, I'm referring to the angle, not necessarily the vector, because if you look at this vector v right here, this is clearly in quadrants 2 and 3, but the angle that we'd be looking at, the angle is actually pointing towards the first quadrant, so this is still a first quadrant angle, even though the vector itself isn't in that quadrant. You with me on that? So when I say what quadrant's it in, referring to the angle, not the vector, because we don't always know exactly where the vector is anyway. Okay, we good with that? All right, so let's look at number 7. On number 7, I have to give the component form, magnitude, and direction angle. So they give me these points. So from that, I'm going to find my component form. So that's going to be -4 minus 9, which is a -13. And -1 minus a -3, which is 2. So my component form is AB, and this is -13, 2. So my magnitude of AB is equal to the square root of -13 squared plus 2 squared. And again, I wouldn't type in the negatives, but you can type it in just like that. You should get square root of 173. So then the magnitude of AB is equal to the square root 173. All right, so what quadrant would this angle be in? Second, okay. Oh, and the other thing is, usually when I move on to, something else or whatever, I've used these points. I needed them to find that component form, but a lot of times I'll go and mark them out so I don't accidentally use those points for something. Like I needed them for the component form, that's all I needed them for. I don't need them for my square root, I don't need them for my angle, anything like that. So then I can get theta is equal to the tangent inverse of 2 over -13. That's not what I type in the calculator, but that's what I write down because that's what I'm finding, right? That's going to give me an alpha value of 8.7 something. And what do I do with alpha to get theta? Subtract it from 180. Good. So that means then that I'm going to get theta 171.254 degrees. Okay. What questions you got? All right, so then we're going to do some of number 8, but not all of number 8, because I don't think we need to keep doing the same thing over and over again. But if you have a vector, I want you to be able to get a component form from a picture. And to write the component form, so this is vector C. Oh, that does not look like a C. C. All right, so my vector form is a pointy bracket form. You count it just like you do slope. Here's where I start. I'm going to go to the right. 1, 2, 3, 4, 5. Since I went to the right, it's positive. So it's a positive 5. And then I go down 1, 2, 3. That makes that a negative 3. That's my component form. Okay. Then from that, you're going to find, you can find magnitude and everything. What quadrant is my angle in? Fourth. The vector is not in the fourth quadrant, right? But we don't care. When we look at the angle, we're looking at, this is where the angle is, right there, fourth quadrant, okay? So this is a quadrant 4 angle, and you would take that into account when you do your thing, which I think you're capable of doing. We good? Okay, so let's look at more with equivalent vectors. So vectors are equivalent if and only if they have the same component form. So these vectors are given to us with their ordered pairs. So we're going to quickly, not that you have to do this every time, but on number 9, we're just going to quickly and very roughly plot where these are. Not even going to put hash marks on here. So if point A is at negative 3, 6, put a point right about there, and B is at negative 7, negative 2, then AB is somewhere kind of like that. Okay. CD, so I'm going to go to 3, negative 1, that looks good. And then negative 1, negative 9, that looks good. Well, it doesn't look good, but it's good enough what we're doing. So I would think, I mean, my know that I am not accurate at all. But I have a chance of these actually being equivalent, right? But I wanted you to see that their location doesn't matter. They could have the same component form, even if they're ordered pairs. When you look at it, you don't necessarily know that. So let's actually go do this the way that we're really supposed to do it. So AB as a component form, it's going to be negative 7 minus a negative 3, so that's negative 4. Negative 2 minus 6, that's negative 8. By itself, that tells me nothing. I have to have something to compare it to. So here is CD. I would do negative 1 minus 3, that is negative 4. And negative 9 minus a negative 1, that's a negative 8. So they do have the same component form, and maybe your picture looked better than mine did. Mine looked really good last period, like I wasn't even necessarily trying harder. But clearly, they have the same component form, which means that AB, vector AB, is equivalent to vector CD. You do not have to plot those when you do them. I was just trying to show you that they're in different locations and it doesn't matter. Okay, we good? All right, then y'all do number 10. So they come out different, right? Which means they are not equivalent, and that's all it's asking us for. So this is how you write that they are equivalent. That's how you write that they're not equivalent. What questions do you have? We good? All right, so you got about 15 minutes to work, and your assignment is in Delta Math, so make good use of your time.